Good evening, guys. My topic for this evening will be still plane areas, plane area trapezoid. By using integration, we will derive the formula for taking the area of a trapezoid who's got a dimension of B1, B2, and H. Okay, let's proceed with the explanation. This is now lesson number 52, plane area, trapezoid. By using integration, we will derive the formula for taking the area of a trapezoid. Trapezoid, it is something like this, guys. I will cross-hatch it. That's a trapezoid. The dimension of the trapezoid is base 1, the upper base. The lower base is base 2. Base 2. The longer base. The height is actually h. This is an isosceles trapezoid, meaning it's symmetrical. This triangle portion on the left will be equal to the triangle portion on the right. It's symmetrical. We will derive the formula. I will give you the formula now. Then later on, we will try to see if this formula is what comes out in our solution. Area for a trapezoid is 1/2 base 1 plus base 2 times h. The problem is actually to derive this one by using integration. We are using this formula under lower mathematics, that is area of a trapezoid is 1/2 base 1 plus base 2 times h. But we do not know where it came from. Actually, this formula was derived using integral calculus. Okay, let's proceed with the solution. Solve figures. Okay. I will bring out the left triangle, the one on the left. The one on the left. Sorry for that one. The one on the left. This one. Okay. So if I will try to enlarge it, this triangle on the left will be this. And by using horizontal slice, okay, this is our horizontal slice, the thickness will be dy. The x here will be xr, and the x here will be xl. The x on the right is the abscissa of this vertical line, and the x on the left is the abscissa of the hypotenuse. We got a problem here. Why? The abscissa of the hypotenuse is variable. Okay? From this point going to the right, actually the variable, the value of y is actually changing. It's variable, so it's a little bit complicated. It's not so complicated because it was a straight line. Okay? So this point here refers to xr with respect to 0, 0, and this point here is xl with respect to 0, 0. Okay? I will place this as angle theta. This is actually A. I introduce a new variable here. It's not a variable, new constant, new dimension. It was not on the original trapezoid, but for the meantime, I will try to represent this portion here as simply A. Okay, simply A. This is A. Okay, it's not on the dimension of the trapezoid, but as a part of the solution, I will place it as A. Okay, this is H, this is A, this is XL, and this is Y. Okay, so to derive the relation, tangent of this angle is this side here over this, or tangent of this angle by using the bigger right triangle is this side here, all over this. So actually, tangent of theta is y over xl equal to h over a. y over xl over, equal to h over a. This is h over a. Solving for xl will be a over h times y, equation number 1. We draw the horizontal slice. I enlarge it here a little bit. The overall length of the horizontal slice is xr minus xl, and the thickness is dy. Okay, but what is xr? This xr here is actually constant. From this point up to this point, it does not vary. Okay, so the equation of this is xr is equal to a, equal to this dimension. From this point here up to this xr is not changing. It is a straight line, and the equation is actually xr is equal to a. This is actually a straight line, and it is constant. Okay? Oh, I will place it now. Differential area over 1 over 2. What is area 1? Okay, see the figure, guys. The triangle on the left will be area 1 over 2. The triangle on the right rather, is area 1 over 2 also. The sum of area 1 over 2 plus area 1 over 2 is actually the sum of these two triangles. So actually, I don't have to think about this triangle here. Just take the area of the triangle on the left, divide it by 2, to include this one. That's why there is an over 2 over there. Meaning to take the total area of the left triangle and right triangle, okay, you just multiply this by 2. Okay? So the area of the left and right triangle is differential area 1 equal to 2. So you know where these two came from, okay? Times the quantity xr is actually a minus xl. xl is actually this one. A over h y plus quantity times dy. Okay? Differential area 1 will be equal to this. So if we try to take the integral of both sides, to compute for area 1, take the integral of both sides. This is with the limit from 0 to h. Our differential y, to cover up the total area of the triangle on the left, should move from this point here up to this. The ordinate here is 0, the ordinate here is h, so the limit is actually from 0 to h. Area 1 now will be equal to 2, the integral from 0 to h of the quantity a minus a over h y plus quantity times dy. Integrating. Area 1 now will be 2. The integral of a times dy will be a, the integral of dy. The integral of dy is y. Okay? Minus the second part, a over h. The integral of y dy, it falls under the power formula. This should be y squared over 2 plus quantity with the limit from 0 to h. Okay? So actually the integration for this is not so hard. The only problem is the formulation of the equation and how to bring out the differential area. Okay? Therefore, area 1 now, substituting values, it should be 2 times the quantity. If y is h, this should be eh minus, okay, a over h. If we replace y by a h squared, this will become h squared over 2. So there is an over 2 over here. Simplifying this one, eh times 2h is actually 2eh squared minus eh squared all over 2h. And luckily, these two here cancel with this. Okay? We got 1h on top. Okay? Because this will be eh times h all over h. So this cancels out. So area 1 is actually eh. Okay, let's try to verify if the area of, if area number 1 really the product of eh. Actually, this is the left triangle. This is the right triangle, and if we try to put on top this right triangle on top, they're similar, okay? This is H and this is A. So to take the total area 1, total area 1 is this. It's just a rectangle. It is the product of A times H. So this should be correct. Okay? So actually, this is a solution by parts. Okay? Okay, let's bring out the rectangle portion. The rectangle portion is this one. I will erase this one. I will erase this one. Let's consider this portion here. Because to take the total area of the trapezoid, it should be the area of the two right triangles plus the area of the rectangle portion. Okay? This here, it got also an XR. This portion here, it got an XL. So if we try to bring out the horizontal slice will be, it is similar to the first one. XR minus XL times dy. Sorry for that one. This is another XR and XL because for the meantime, we are considering the rectangle portion. XR from the figure is actually A plus B1. Why A plus B1? XR here, this is A and this is B1. So this XR here is equal to A plus B1. And XL is actually A. That is A. Okay? So actually, these two equations was derived by going back to the figure. Okay? XR will be A plus B1, XL will be equal to A. Therefore, if we try to represent the area of the second horizontal strip as area 2, differential area 2 now, this differential, equal to XR. XR is A plus B1 minus XL minus A, close quantity times dy. Actually, this A here cancel with this. Differential area 2 will just be simply B1 times dy. Then to bring out area 2, to compute for the area of the rectangle portion, try to integrate both sides. Okay? The integral of differential of area 2 is just area 2 equal to the integral from 0 to h of B1 dy. B1 is constant. We bring it out. The integral of dy is just y with the limit from 0 to h. Placing the limits, it will be B1 times h, that's the upper limit. B1 times 0 will be 0, or this will now be 0. So area 2 is actually B1 times h. Okay, let's try to verify if area 2 is actually the product of B1 times h. The rectangle portion, this is B1, and this is h. Okay? And total area 2 is this one. So it's a rectangle, right? The area of a rectangle is B1 times h. So this must be the correct answer for the rectangle portion. It's correct. So to compute the total area of the trapezoid, it will be equal to area 1 plus area 2. Why area 1 plus area 2? Area 1 is the two right triangles. Area 2 is the rectangle portion. So we just add up those one, guys. So it will be, what's area 1? It is EH. It is EH. And what is area 2? It is B1 times H. Okay? But I actually introduced A over here. So I will try to bring out A as a function of B2 and B1. Okay? How could we find the relation? Okay, I'll try to go back to the figure. This portion here is actually same as this one, right? this portion here is actually the lower base minus the upper base minus the upper base. They are equals, right? So this is divided by 2. And that is actually equal to A. We place A to be B2 minus B1 over 2 back to the final equation. So this should be B2 minus B1 over 2 times H. We are following this. Plus B1 times H. And if you try to simplify this one, guys, what will come out will be total area equal to, it's just an algebra. I will give you the final answer now. It is 1/2 the quantity base 1 plus base 2 close quantity times H. It is same as this one. So actually, how the area of the trapezoid was derived, it is actually, the solution is something like this. So whenever you are trying to solve the area of a trapezoid in which we are given base 1, we are given base 2 and H, to take the total area, just use this formula. Total area will be 1/2 the quantity base 1 plus base 2 times H. Actually, this figure, guys, is something like, if we try to invert this one, it seems it's just like, the one they are using for flood control. Okay, the area of this flood control, right? Actually, the configuration of the flood control canal is actually a trapezoid, inverted trapezoid. So if you want to compute the volume of the water running at any given moment, if you are given base 1, we are given base 2, and you are given the height, for a certain length on the canal, actually you could compute how much will be the volume of the water at any time. Okay, guys, that's the derivation for taking the area of a trapezoid. Good evening.